Okay, this is the 32nd lecture, and our topic today is FIR lattice synthesis. In the last lecture, we had taken an example of IIR, all pass realization by lattice. Then we talked about tunable filters, low pass, high pass combination and band pass, band stop combination. And then we looked into the realization of an arbitrary IIR transfer function by lattice, by tapped lattice, that is the lattice realizes the all pass constructed with the same denominator, and then take taps and weigh the signals, add them together to get the desired transfer function. We showed that this is possible in all cases, and then we concluded with an example. We also started our discussion on FIR lattice, and the procedure for FIR lattice is synthesis by analysis. This is the traditional approach. We can also proceed from synthetic point of view. The procedure seems to be quite complicated. Matrix decomposition and then matrix synthesis is required for that. So, our structure is this, where instead of my notations are sigma sign for summation, Mitra uses plus sign, and my notation for a multiplier is a circle. I did not want to draw a triangle every time. Except for this, it is the same structure that I drew last time. I drew in terms of boxes. I require this total diagram to be able to illustrate some points. First, you notice that in this diagram, the total number of delays is capital M. Okay, first, second, and the 0th, first, M minus 1th, and therefore capital M number of delays. So, the highest power in the transfer function, the degree of the transfer function should be capital M, okay, number 1. Number 2, since there is no feedback, it should be an FIR transfer function, no feedback, it is all feed forward. Number 3, the constant term in the transfer function, that is the term which does not involve any delay, should be equal to 1. This is my output. This is my output y of z, and you see that there is a straight path from the input to the output. This output is not important at this point, we may be able to utilize it later. But you notice that if constructed or fabricated on a chip, this will also be a multifunction chip. Not only we get the FIR function here, we get other FIR functions at the various nodes. So, it is also a multifunction chip. And finally, h of z, the transfer function, which is capital Xm of z, we shall call this Hm of z, divided by x0 of z. Obviously, the constant term is 1, no delay, and the term with the highest delay, that is z to the minus m, obviously has to be gone like this. It has to go totally in the lower path and finally come through Km multiplier to the output. So, the coefficient of z to the minus m must be Km, all right. In between we have other impulse response coefficients which can also be calculated from the diagram. For example, if you want the coefficient of z inverse, then the first term is K1, second term would be you come like this, then you go like this, right. So, K2, no, if I want the coefficient of K1 z inverse, then I come like this z inverse, and go like this. So, it would be K1 plus next term would be K1 multiplied by K2, because you have to come like this, then traverse this. Then the next term would be K1, K2, K3 and so on and so forth. You can do this, but this is not helpful for synthesis. In the synthesis, then you shall have to solve a set of nonlinear equations, which is very, very cumbersome. So, we follow an alternative procedure, and and to start with, we say that this is H1 Z inverse plus etc. plus, let us call this as HM to start with. From the analysis, it is clear that Km is equal to Hm. Km is the parameter of the last lattice, is equal to Hm, but let us start with this, and therefore, we say that our desired transfer function Hm of Z is equal to 1 plus summation Hn Z to the minus n equal to 1 to capital M. This is what we wish to synthesize. We also take the notation that Hiz we define as capital Xiz divided by capital X0z. That is, Hiz is the transfer function from the input to x1, x2, etc. Okay. So, that H capital Mz is the desired transfer function, but in between you get a lot of transfer function. The transfer function between x0 and x1 is not 1, because one comes straight, the other comes like this. Okay. So, these transfer functions H1, H2, etc. are also useful. In fact, you get twice m number of different transfer functions. It is a multifunction. We also define the lower signal transfer functions with a prime, that is, we say Hi prime z equal to Xi prime z divided by X0 z, okay, which makes Hmz as the desired transfer function. Also, you see H0 z is equal to H0 prime z should be equal to 1. The transfer function should be equal to 1 if I put I equal to 0. From x0 to x0, obviously it has to be 1. Okay. Now, if we look at this diagram and try to construct the first few signals, capital X1 for example, capital X1 is X0 plus Z inverse K1 X0. Therefore, capital X1Z equal to X0Z plus K1 Z inverse X0Z. And similarly, capital X1 prime Z, if I look at the diagram, it shall be K1 X0Z plus Z inverse X0Z. In other words, H1Z shall be equal to 1 plus K1 Z inverse, right, and H1 prime Z shall be equal to K1 plus Z inverse, right. Now, don't you see that the ratio of the two is an all pass function? You see, it is very intimately related to all pass. But something to notice is that, well, since I have already said the ratio of the two is an all pass function, obviously this can be written as Z inverse H1 of Z inverse. Agreed? This is the relationship between H1 prime and H1. In a similar manner, I can write x2z. If I want to construct x2z, it is x1z plus, look at the diagram, x1z plus k2z inverse, yes, x1 prime z, all right, k2z inverse x1 prime z, and x2 prime z is equal to k2 x1z plus z inverse x1 prime z. All right, I am proceeding very slowly, very slowly. It is important that you understand the beauty and the elegance of this derivation. And from here I can write the two transfer functions h2 of z and h2 prime z. You look at what the transfer functions. h2z is equal to h1z, x1 by x0 is h1, plus k2z inverse h1 prime z, right, and h2 prime z shall be equal to k2 h1z plus z inverse h1 prime z. If you combine, here also you see there is a all pass kind of relationship between the two. If you combine this with the fact that h1 prime z is equal to z inverse h1 of z inverse, all right, then you get h2z, then you can get rid of the primes, okay. Then you get h2z as h1z plus k2 z to the minus 2 h1 of z inverse, agreed, and h2 prime z as equal to k2 h1z plus z to the minus 2, right, h1 prime z is equal to z inverse this, z to the minus 2 h1 of z inverse. Don't you see that this is the same as z to the minus 2, yes, h2 of z inverse, isn't that right? If you take h2 z inverse and multiply by z to the minus 2, you will get exactly this, all right. And by induction, what has been shown true for I equal to 1 and 2, by induction you can show that Hiz is equal to Hi minus 1z. Well, first let us write the equation in terms of primes, then we shall write the other equation also. It would be k I z inverse, then Hi minus 1 prime z, agreed, and Hi prime z would be equal to ki Hi minus 1 z plus z inverse Hi minus 1 prime z, okay. These are not by induction, these are from the diagram, but by induction you can show that Hi prime z is equal to z to the minus I Hi z inverse, okay. We showed it for I equal to 1 and I equal to 2. Assume that this is true for I minus 1, then you prove that this is valid for I also. So, this is a result to be remembered, we shall require this later. One, and the other result is if I substitute this here, then I get Hiz as equal to h I minus 1 z plus what do I get? K I z to the minus 1 multiplied by z to the minus I minus 1. So, it would be K I z to the minus I. Is the point clear? Z inverse, and from here h I minus 1. So, it would be z to the minus I minus 1. So, the product would be z to the minus I, then h I minus 1 z inverse. This is another result which we shall use later. Very good. These two equations describe what there is in this structure, in this modular structure. Now, this is not what we want to do. So far what we have derived is analysis. If we know h I minus 1, then you can find out h I. Okay? That is not what we want to do. What we want to do is, given h m, we want to find out the k m's. That is right. So, that is the synthesis problem. So, we should proceed in the reverse fashion, that is, starting from h m, we should be able to derive h m minus 1, h m minus 2, because for h m you have already seen that k m is equal to small h subscript capital M. So, if you find capital H m minus 1, then you can find k subscript small m minus 1, and so on and so forth. Okay. So, we should proceed in the reverse direction. We should start from h m and then successively by an iterative method, that is what we are looking for, derive the values of k m minus 1 up to k 1, because k 0 has already been made a short circuit. X 0 and x 0 prime are the same. Okay. Now, to that end in view, what we do is we put I equal to m here to be able to derive h m minus 1 in terms of h m. Let us put I equal to m and let us see what the result is. We shall get h m minus 1, no, h m z as equal to h m minus 1 z plus k I z inverse k m, that is right, k m z inverse h, pardon me? Z minus m. No, I am using the first relation still. I will make use of this later. I am using the first relation. Okay. I can do that here also, but let us not complicate things. Okay. There is a point which I want to illustrate with this. H m minus 1 prime z, and then h m prime z is equal to k m h m minus 1 z plus z inverse h m minus 1 prime z. All right. Let us do this. We multiply this second relation by k m. Okay. Then you get rid of the primed quantities. Agreed? We did not have to replace prime by unprimed quantity, because we want to get rid of this. Our aim is to obtain h m minus 1. So, we get rid of this, you multiply by k m and then subtract from the first relation. That gives you h m minus 1 z as equal to 1 by, if you multiply this by k m, then you get k m squared. So, 1 by 1 minus k m squared, you see this nuisance has already started showing its teeth. If k m is equal to 1, you are nowhere. Okay? And very surprisingly, not a single textbook, there must be about 132 written so far, that was my last count, not one of them mention this difficulty. What happens if the last coefficient is 1? No, they do not mention. This is what this small paper, I wrote a I wrote a sophisticated paper for IEE, but then I wrote a simpler one for students. This is what I have given to him. You will get the paper, you will get a copy of this. So, what do we get here? HMZ minus Km HM prime Z. Agreed? We have not yet gotten rid of Hm prime. It is at this point that we get rid of it. That is, we write this as 1 minus Km square HMZ minus, what do we get here? Km Z to the minus M Hm of Z inverse. Okay? Right?
Why would it be Z to power minus M?
Oh, because we showed this is the relation that I use now. We showed that Hi prime Z is Z to the minus I Hi Z inverse. Okay? Right? So far so good. Now what I do is I replace HMZ by its expanded form. Okay? That is, I write Hm minus 1Z as equal to 1 by 1 minus Km squared. HMZ is 1 plus H1 Z inverse plus H2 Z to the minus 2 plus etc. plus Hm Z to the minus M, then minus Km. If I multiply Hm of Z, that is this quantity, by Z to the minus M, what do I get? I get a reversal of the coefficients. So, what I get is Km multiplied by Hm plus Hm minus 1 Z inverse plus Hm minus 2 Z to the minus 2 and so on, plus H1 Z to the minus M minus 1 plus Z to the minus M. I have made a mistake. Have I? Good. I haven't made a mistake. All right. So, I collect the coefficients now. So, I get 1 minus Km square. The constant term will be 1 minus Km Hm plus H1 minus Km Hm minus 1 Z inverse plus H2 minus Km Hm minus 2 Z inverse yes plus etc. What would be the last term? Hm minus Z to the minus 2, yes. Please make this correction. Hm minus Km Z to the minus M. All right? Yes. This shows that if Hm minus 1 is to be of order capital M minus 1, then this term should vanish. That is, Km should be equal to Hm, which means that we are making progress. This result was available from analysis, but for synthesis also, that is for going from capital M to M minus 1, we required this result. So, we are making progress. So, our major conclusion now is that Km should be equal to Hm, the coefficient of the highest power term, and under this condition, if Km equal to Hm minus 1Z is of order capital M minus 1 and can be written with a constant term of if Km equal to Hm, then this is 1 minus Km squared, 1 minus Km squared. So, constant term shall be 1. We are making progress. Hm minus 1 is of the same form as Hm, and therefore, iteration can be used. 1 plus, let us call the other coefficients by a prime, h1 prime z inverse plus h2 prime z inverse z to the minus 2 plus etc. plus h m minus 1 prime z to the minus m minus 1. Agreed? This is the form where, very interestingly, the coefficients h I prime, if you look at h 1 prime and h 2 prime, you notice that these coefficients are h I minus k m h m minus I divided by 1 minus k m square. Don't we know this relationship? It is the same relationship as used for IIR all pass designs. Okay? You see the elegance of the method. Okay? So it is the same relationship. Once you know this, it is applicable for FIR, it is applicable for IIR also. In IIR it is only all pass, in FIR it is an arbitrary transfer function except Km equal to 1. And if I have obtained Hm minus 1, okay, what is now the Km minus 1 obviously is equal to H m minus 1 prime. Then the next step would be you derive H m minus 2, from which you derive Km minus 2 and repeat till you exhaust the function, and you have obtained all the coefficients, all the lattice coefficients. Okay. Now let's look at an example. Is the procedure clear? Okay. Let's look at an example. Let h3z, a third order function, be equal to 1 plus 3/4 plus half z to the minus 2 plus 1/4 z to the minus 3. If you recall, this is the same, it was the denominator of an example that you worked out in the last lecture. Okay? And since the recursion relationship is the same except that d's have been replaced by h, that is all, and therefore our lattice parameter should be the same. We would start from k1, we would start from k3, k3 would be equal to 1/4, then go backwards k2 and k1. Now what were the lattice parameters? We can draw the structure now, feed forward k1, k2 and k3, no short circuit here, okay, that is the difference. The output is here. There is an output here which we shall investigate later, but this is not of interest now to realize this. And at the input shorted, okay, there are two inputs to k1, and k3 is obvious, 1/4. K2 and K1 we had calculated earlier. K1 is half and K2 is 1/3. Is that right? K2 is 1/3. So we don't have to do anything. This is why I took that particular example as the same denominator, same transfer function. Now we come to the $1 million question: what happens if Km is equal to 1? Not only Km equal to 1, if at any intermediate stage, if Ki becomes 1, then you cannot proceed to the next stage. Is that right? Okay. Now the general case of Km equal to 1 we shall take a little later, but first let us look at linear phase transfer functions. Linear phase FIR transfer functions. As you know, this has also not been treated in any textbook. I have not found in any journal either a paper on this. That is why I started working a couple of years ago. It takes about 2 years to publish a paper. But this paper that I have circulated was written specially for students of the last batch who said, "You don't want to read this sophisticated paper, why don't you write a smaller, simpler article?" Now, even this case has not been treated in the literature, how to synthesize, because in a linear phase transfer function, you know, the first coefficient, if we start with 1, then the last coefficient has to be +1 or -1, and it's the same problem. 1 minus km squared is 0. Okay. So, we shall, instead of doing the general procedure, you can generalize later, we will take some examples. You know, there are 4 cases of linear phase FIR: even length symmetrical impulse response, even odd length symmetrical impulse response, then even length asymmetrical, and even length odd length asymmetrical. Okay, we will take an example of each case, because each case has a characteristic of its own. We cannot generalize by doing only one case. We will first start with an even length and symmetrical response. H5z is equal to 1 plus H1 z inverse plus H2 z to the minus 2 plus, yes, the length is 6, 1, 2, 3, H2 z to the minus 2, 3 plus H1 z to the minus 4 plus z to the minus 5. Okay. And you see, in order to derive H4 from it, we shall not go according to K5 equal to 1. Well, K5 equal to 1 is a fact, but we cannot use the recursion relation. Therefore, we will do something else, and it's a rather odd coincidence that it struck me during a morning walk that you could use this relationship. What was this? This relationship to derive the lower order transfer function. After all, this we have proved. Okay. So, if I write here H5z, and that is how the problem got solved, H4z plus K5 is 1, K5 is 1. So, z to the minus 5 H4 of z inverse. Agreed? Now, if I write this, if I write H5z, the given H5z, if I decompose like this, 1 plus H1 z inverse plus H2 z to the minus 2, the other 3 terms can I write like this: z to the minus 5, z to the minus 5, 1 plus H1z plus H2z squared, right? Isn't my H4z obvious now? If you compare these two, you get H4z as equal to 1 plus H1z inverse plus H2 z to the minus 2. It is a 4th degree transfer function, but fortunately we have only up to degree 2. It should happen because of symmetrical coefficients. We have seen that the number of multipliers can be reduced by approximately by a factor of half. So, this is also a corroboration of the fact that the number of multipliers is being reduced. This is equal to H2 of z. From 5 we have gone to 2. What does this mean in terms of the lattice coefficients? That is, what is K4? You see, from H2z we will be able to obtain K2 and K1, but what is K3 and K4? 0. Agreed? Which means that instead of these 2 blocks we shall simply have the delays Z inverse, Z inverse. Is that clear? So,
while writing H4z as 1 plus H1z inverse plus H2z minus 2,
yes,
we have reduced the next 2 to equal to 0.
That's
Means it's not linear phase now.
this is not, I don't require. My original transfer function is linear phase. There is no guarantee that in between we shall get linear phase. No. In between you may not get linear phase. We shall not in general. Okay, unless it is an odd coincidence. So my conclusion is K4 equal to K3 equal to 0. And since H2Z is equal to 1 plus H1Z inverse plus H2Z to the minus 2, K2 is obvious equal to H2. And isn't K1 also obvious? If you remember, D1 prime should be equal to D1 divided by 1 plus D2. So K1 should be equal to H1 divided by 1 plus H2. And the synthesis is complete. Okay? Would you agree that this is also a very elegant solution in general? Okay. Yes.
So how can we write this H4Z equal to H2Z, because the first three terms of H5Z they will make H2Z, then the first five terms of H5Z will be H4Z.
No. H4Z is a derived transfer function from H5. It is H4Z plus Z to the minus 5 1 plus Z to the minus 5 H4Z inverse. It just turns out that H3 and H4 for H4Z are 0. So it has, in one step, it has reduced to a second order transfer function. Okay? And that is how K3 and K4 were equal to 0. So my diagram now becomes, I think I missed the diagram. Well, doesn't matter. What I have is, I have an x of z the first block is K1, that is K1 equal to H1 divided by 1 plus H2. The next block is K2, which is equal to H2, and then K3 and K4 are 0. So what we shall have here is Z inverse, no crisscross, they are 0. The next one is also a Z inverse, K3, K4, no crisscross, and this goes, and then finally we have a K5 equal to 1. This is the output.
So is that a lattice structure?
Which
Because
one?
You don't have the same thing repeated.
Yes, it is lattice, except that you don't require to fabricate these lines. That's it. These lines in the processing step, you just omit at the third step these lines, or put K3 equal to 0, because there is a crisscross here, K3, K3 in the forward direction. Put K3 equal to 0, which will be translated by your software for fabrication as no lines there. Okay, so it simplifies. Now you see the number of multipliers. Number of multipliers is twice 2 here, 2 and 2, 6, which should have been 3 in canonic. Okay, should have been 3. But can you have a single multiplier realization of FIR lattice plot? We can have FIR lattice plot. We did it for IIR. That's an open problem till now. Okay, we might solve it later. Now let's take the second case. In the second case, we have symmetrical impulse response of odd length. So let's take a H4Z. Second case, symmetrical impulse response of odd length. Length is 5, so I get 1 plus H1Z inverse plus H2Z to the minus 2. Now this is the central term now. because I shall have a z to the minus 4 here plus h1 z inverse z to the minus 3 yes. Okay, this is the central term. Now how to decompose? Since I want to write this as h3z plus k4 z to the minus 4 h3 z inverse, agree?
Yes.
K4 is 1. I want to write it in this form. I must have the same number of terms here and here, same number of terms. Now if I take this, then I shall be left with 2 terms. So obviously the choice should be you split this into 2 equal halves. So you write this as 1 plus h1 z inverse plus h2 by 2 z to the minus 2 plus z to the minus 4 1 plus h1 z plus h2 by 2 z squared. Okay, and the identification of h3 is obvious now. h3z is equal to 1 plus h1 z inverse plus h2 by 2 z to the minus 2, which incidentally is a second order transfer function. So I have been able to reduce the order by 1. The conclusion is that K3 is equal to 0. Agreed? K3 equal to 0, and K2 is also obvious, H2 by 2, and K1 is also obvious. Okay. K1 shall be equal to H1 divided by 1 plus H2 by 2, and the synthesis is complete. So the diagram would be X K1, then K2, then a Z inverse, no crisscross, finally K4 equal to 1. This is the output. All right. There is no reason why you cannot extend it to any order that you like. Let us look at the other two. That is case 3, a symmetrical impulse response, even length. A symmetrical impulse response of even length, which means that if I take even length, I take still a fifth order. Fifth order is respectable enough, it is not a trivial case. So I take 1 plus h1 z inverse plus h2 z to the minus 2 minus asymmetrical, so h2 z to the minus 3 minus h1 z to the minus 4 minus z to the minus 5. So K5 is equal to minus 1. And you notice that if I want to write this as h4z plus K5 z to the minus 5, not 4, h4 z inverse, and since K5 is minus 1, I want to write this as equal to h4z minus z to the minus 5 h4z inverse, and by rewriting this you can show that 1 plus h1 z inverse plus h2 z to the minus 2 minus z to the minus 5, what shall I have inside? The same term, 1 plus h1 z inverse plus h2 z plus h2 z squared. Okay. What does it mean? That the realization is identical to the previous case, except that the last lattice coefficient shall be minus 1. instead of plus 1. Agreed? Okay. So, if you know how to do it for asymmetrical, symmetrical, you know for asymmetrical. The situation is slightly different if it is asymmetrical and odd length. Now, look at this. The middle coefficient is 0. Okay. Asymmetrical Hn and odd length, that is, we take again H4z. So, we shall have 1 plus H1z inverse. The middle term now has to be identically equal to 0. So, I shall have minus, wait a second, minus H1 z to the minus 3 minus z to the minus 4. And obviously, I can write this as 1 plus H1 z inverse minus z to the minus 4 1 plus H1 z. All right? Why does the minus sign come? Because K4 is equal to minus 1. K4 is equal to minus 1. Therefore, H3z is equal to 1 plus H1z inverse, which is H1z. Therefore, K3 equal to K2 is equal to 0 and K1 equal to H1. No calculation, it is by observation. And the the diagram for this case, very simple to draw. We shall have only one complete lattice, that is K1, K1 equal to H1, then K2 and K3 both are 0. So, we shall have Z inverse, and finally K4 equal to minus 1. The job is done. This is the output, y of z, x of z. So, we have been able to complete all the 4 cases, and linear phase, it will use the same number of multipliers as direct canonic structure, approximately half the number of multipliers if a lattice can be realized with a single multiplier. Okay? If a lattice can be realized with a single multiplier, then the structure will also be canonic. It is now time to go to general transfer function with the coefficient, last coefficient equal to plus 1 or minus 1. Once again, let us take we shall have to consider even length plus 1, odd length plus 1, then even length even length minus 1 and odd length minus 1. Okay. Let us start with plus 1. We take, to bring variety into experience, we take odd length, a general transfer function, not necessarily linear phase. I have 1 plus H1 z inverse plus H2 z to the minus 2 plus H3 z to the minus 3 plus z to the minus 4. Okay. The last coefficient is 1. There is no symmetry or anti-symmetry in the given structures. I am tempted to go back and point out something. I will do that later. Let me complete this case. I have time today. Yes. Okay. So, what we do is the following. After all, what we are interested in is to avoid this K4 equal to 1. We want to avoid this recursion. Okay. So, what we do is we first write this, as sum of a linear phase function plus whatever is left, and to minimize the number of delays in the linear phase function we take all the highest powers, which means that we take 1, we take z to the minus 4, 1 and 1, then we take h3 z to the minus 3, we take the complete term here, and we take h3 z to the minus 1, alright. Then I must subtract something, I will do that later, and h2 is a middle term, so I take h2 z to the minus 2, this is the linear phase. What am I left to it?
Minus h1 minus h3.
Plus h1 minus h3 z inverse. Agreed? Now this, anything else? That's all. I have taken the h3 completely, I have taken up to h2, only h1 I changed to h3. Now this we have already realized, this we have already realized, where this was not h3, it was h1. Agreed? So you can realize this. Now in that realization, that is not enough, you have to make a parallel branch now, in which this transfer function is h1 minus h3 z inverse. This is also linear phase. Okay? Z inverse is a linear phase, it is a trivial FIR linear phase. But where would you pick up after the first delay? That is, you have a Z inverse in the first K1 block, you have a Z inverse to start with. After this, you take a tap, multiply by h1 minus h3 and add it to the main lattice output. Okay? So that is how you take care of a general transfer function in which the last coefficient is plus 1. Yes.
Can you show this thing in the context of the earlier figure?
Can I show this thing in the context of the earlier figure? Okay. It's that I have to draw.
Just show the earlier figure that we have drawn where that we take the tap from.
Yeah, but earlier figure showed a box with K1. I have to show Z inverse. Okay, if that is what you want, let me draw this completely. X of Z, then Z inverse, then you have a crisscross. Okay. Let us show this, he wants it, so I will do that. This is K1 and this is also K1. Please draw with me. Okay. This is the first block. Now I am free to draw the second block as K2. I do not require any more delays. I had to show this explicitly, and then Z inverse, that is correct, and finally K4 equal to 1. This was the earlier diagram, except that this whole thing was put in a block marked K1, and this is my output. I do not require this output now. Then I take a tap from here, multiply by h1 minus h3 and add it to here to get my output y. Okay, since you insisted. Now I want to go back a little bit to point out that one of the students in the last year's batch, he gave an alternative. Let me take the first case. What was the first case? Even length? Symmetrical impulse response. Okay. Yes. That is h5z equal to 1 plus h1z inverse plus h2z to the minus 2 plus h2 z to the minus 2 plus h1 z to the minus 4 plus z to the minus 5. Okay. minus, I beg your pardon, minus 3 minus 4. This 4 was all right. Now he pointed out something very interesting. He said, if I want H4Z, well, my Hi prime shall be equal to Hi minus Ki H m minus I, then this should be Km. Oh, well, H4. So let us say Hi prime equal to Hi minus K4, which is 1, not K4, K5, which is plus 1. So it will be H minus H 5 minus I divided by 1 minus. Okay, let's write this K5. Okay, let's not put the value of K5. This is what the student pointed out, and you must appreciate, I did. What he said is, please don't bother what K5 is. That K5 is 1, don't put it here because you get a 0 by 0 form, because Hi is the same as H5 minus I. Isn't that right? Yes. And therefore this is equal to K5, this is equal to Hi divided by 1 plus K5. Now put the value of K5. Do you appreciate the point? Because of symmetry. Well, if it was anti-symmetrical, then instead of minus sign it would have been the plus sign, and even then, huh?
You will get it.
Suppose H5 minus I was equal to minus Hi.
Yes, sir.
Then it would come.
Then also it would come?
Yes, sir.
The same relation. This is what he pointed out. So there is no problem. You can go from H5 to H4. Okay? And it turns out that H4, what would this be? This is simply Hi by 2. Agree? So H4 of Z would be equal to 1 plus H1 by 2 Z inverse plus H2 by 2. It's very interesting alternative. H3 by 2 Z to the minus 3 plus H1 by 2 Z to the minus 4. Okay? There is no problem now. You can go ahead.
Sir, how can we cancel?
How can we?
How can we cancel one? We get the Hi upon 1 plus K5.
Oh,
This is possible if K5 is not equal to 1.
if K5 equal to 1 and Hi equal to H5 minus I, which is the condition constraint,
Then
it's
we
a
get
0 by
one.
0 form. It's a 0 by 0 form.
If we take Hi is equal to H5 minus I,
Correct.
okay, we can take a common Hi. We get
That's what I've done. So it is 1 minus K5.
upon 1 minus K5 square.
That's right.
Okay, so we cancel out 1 minus Hi.
No,
That's
no,
why
no,
we
no,
get
no, no. We cancel 1 minus K5. 1 minus K5, 1 plus K5.
Okay.
We cancel this.
We can cancel if K5 is not equal to 1.
Yes, sir.
This is a rule of cancellation.
Okay. You have a point there.
Yes.
Yes, we can cancel only if 1 minus Km is not equal.
That is correct. That is correct. That's one fallacy. The other thing is, even if this is permitted, even if you cancel, he showed by analysis that the result that he gets, the structure that he gets, does realize the transfer function. The taste of pudding is in its eating. So if it works at the final end, this cancellation, even though it was slightly illegal, it gives correct result. We'll continue next time.